Thank you for coming for our second presentation of the day in our group meeting. And now we have me, Leticia, presenting a paper about searching for dark photons and dark scalars decays at electron-positron colliders. So this is a very recent paper. It was from, some days ago. Um, and it focused, as I said, on the search for dark photons at the future electron colliders. Like, oh, sorry, is there? Hi, Gabi.
Hi. Sorry.
No, no worries. At a circular electron-positron collider, that's CEPC, and FCC-ee, that will be the first stage of FCC. If it happens. So these are both future prospects. So the main strategies that they consider in this paper, it will be through displacement vertices for the dark photon. So the range of mass is the range of mass for both the dark photon and the dark scalar would be from 10 to 100 GeV, so in the GeV scale, but in the lighter part. And the search would be mainly for displaced vertices, considering that this dark photon is long-lived. So for it to be long-lived, first they put on the assumption that this mass needs to be small enough for it to be long-lived, but not so small. So they put, because they need to incorporate in the range of the detectors. So they consider a range, let me see, we have in this, yes. They consider a range from 2 GeV for the dark photon up to half of the dark scalar. So let me put here the Feynman diagram. It will be, So the main case that they are looking for is this case. So this dark scalar, it would be a Higgs-like scalar. So it's a singlet added to the standard model, and it will be introduced via the group that is introducing the dark photon as well. So the mass of the dark photon is given by this dark scalar field at the via VEF at the symmetry breaking of the U1 that is inducing this dark photon. So after this U1 dark symmetry breaks, the dark photon gets mass, and when the standard model symmetry breaks as well, they add kinetic mixing of this dark photon to the photon as well, like all of the other dark photon theories. And it introduces as well a mixing between this scalar field and the Higgs field. So due to this mixing, we have an interaction with the scalar field and the Z boson. So considering this mixing is strong enough but not so strong, this process is viable, and they put here. Okay, so this would be the cross section for the case that they're looking for. So electron positron going into Z and scalar field. In the Higgs production machines that they are trying to build, this would be normally a Higgs, but as we're trying to look for new physics, and this scalar field has a mixing with the Higgs. This is viable. So it has a dependence on where it is here. This mixing angle, that is the mixing between these scalar fields, the scalar and the Higgs, which suppresses this cross section. Therefore, it you have a range of for this angle where you don't want this to be so suppressed that it wouldn't be possible and you would never see this process, but you have some bounds as well on this angle that this mixing can't be larger than 10 to minus 1, I think, and 10 to minus 2 for this 10 to 100 GeV. So okay, so considering now this, in this scalar, it promptly decays, as we can see here, is promptly decays in dark photons and fermions. They put this angle here. Yeah, they fix this coupling as well. This would be the coupling with the scalar, dark scalar, and the dark photon. They fix this as 10 to minus 2. And with this, and knowing that this is suppressed by this angle as well, we can suppose that the dark scalar decays mostly in dark photons. That what we are wanting to have. And then because this dark scalar it decays promptly. Let me put in the board because they just put the Feynman diagram separated. So I have here the plus and minus for Z, and then Z. This is our scalar. We are considering that it decays and then produces, but it decays promptly. So I'm just gonna put it here in the different state. This prompt decay, for those who don't know, is just imposing that this life, no, sorry, lifetime, it's too short. So as it is produced, it decays. So it's in the same place where it is produced. It decays approximately. So because when we are looking for displaced vertices, this is the vertex that we're looking for. I mean, no, not this. Then we produce the two dark photons that has mass. They have mass, so it interacts with this. And then we are looking for the displacement in the vertex of these dark photons. So it suppose that when it's produced, you have a space where it travels without decaying, and then it will decay. I will put here, and two fermions. So with this, we can search in the inner tracker of the collider the difference in the place where it was produced and where it decayed. So yeah, we have the technology. I don't know much about it, but I found it very interesting that you can see enough to see where it is produced and infer, this is where it decayed because it produced this final stages. So we would produce fermions in both ends. And the two strategies that they look for in this paper is first looking for just one vertex displacement. So one dark photon producing later on two fermions, and the other one don't care much, or looking for two displaced vertices. So this scalar field can decay in fermions, but it will mostly decay on dark photons. Here you have, okay, if we consider a mass for the dark photon to be too big, it will decay more rapidly. So they focus on two, but we can't consider a mass too small. So they consider 2 GeV up to some GV, but as you can see here, here in the y-axis is the proper decay length. So we have, let me see, here. This is the light velocity. This is proper time, uh, lifetime, and this is the total decay width. So this would be like the length, proportional to the length it travels without decaying. So we can see that it becomes smaller as the mass increases. So we are focusing, it would be best if you had a lighter dark photon mass in this region here. These bumps are because of the inclusion of the tau lepton decay, um, up to some mass. I think here you have 2.5 GeV. It can decay on tau leptons. Oh, sorry, in charm quarks. 3.5 can decay in tau leptons, and then 8.3 decays on boron quarks. These are, in both these graphs, are the same bumps. Here's the branching ratio. Oh, important. This is normalized with the kinetic mixing, just to, so you know. So this would be the length on itself. Okay. So they consider these Feynman diagrams, and then they put on the strategies. This is a scheme on the inner track for both CEPC and FCC-ee. They have a similar geometrical structures and so on. They have, yeah, very, very little differences on, this is the inner ratio on the inner tracker. This is the auto ratio. So this is a cut, vertical cut here. This is the half of the length, total length of the inner tracker. This is the volume. So you can see here that they are pretty similar in these values. But one thing that they have more discrepancy is on the integrated luminosity. Here would be the acceptance formulas for for both of the strategies. Is dependent on the probability of the first one decaying on an inner tracker, and a bunch of statistics. And I'm so sorry, I don't know much about it, so I'm not gonna dive further into this. But this is just relating the acceptances and the probabilities of both displaced vertex or one displaced vertex. So let me put, this would be the probability. I think it's here. Yeah, here. Okay, so for the CEPC, we have 5.6 on integrated luminosity, and we have 22 inverse autobarns, and for FCC-ee we have 5.6. So we have a greater luminosity F at CEPC. And then they inferred, okay, they did the simulations on PITIA and using MedGraph for Monte Carlo simulations as well. So they considered some fixed masses for the scalar field, and for each masses would be these ones. And for each mass, they did a scan over the mass of the dark photon from 2 GeV up to half of the mass for the dark scalar. They fixed both coupling and connect mixing, the coupling and the mixing with the Higgs. And they put here some curves, some ISO curves for the parameter space of the kinetic mixing versus the mass of the dark photon in both these cases. So this is for the first strategy, and later we have the second strategy. So this parameter space, this curve, this almost curved, closed curve, it represents inside here. It would be the allowed parameter space. From up here, from this curve up, we have too small of a um, oh, sorry. Let me just get here. I think we have a higher decay width value because it depends on the kinetic mixing. Let me just check here. Yes, it depends on the kinetic mixing squared. So it would decay too much and too rapidly. So it is not allowed by our standards that we are looking for displaced vertex. And down here we have, I mean, the vertex would be so displaced, it would be too long lived. So it would most probably decay outside of the inner tracker, so we can't detect anything. So the allowed region is just inside these regions here. Each of these curves is considering one value for the mass, and the difference between the solid curves and the dashed ones, point point like ones, is the detector used in the experiment. For first strategy and second strategy is the same. These up here are the bounds the bounds made with LHCb, CMS, and Babar, which are experiments that are already running. So the oh sorry, is there something in there? Okay. So concluding, they conclude that for first strategy, as we are less, it's not less constraining, but less, we are looking for just one vertex, displaced vertex. We have a larger parameter space allowed comparing to the second strategy that we are looking for two displaced vertices. So it would be more difficult to see. Important thing that I forgot to say, this would be this signal, for both strategies, are considered background free from standard model. The second strategy is, of course, background free. The first one, they do some implications, but it's mostly no background from standard model. So there are good signals to search. The center of mass energy would be 240 for both of them. And yeah, it's basically this for the CEPC, as it has a larger integrated luminosity. You have best constrained regions, so I mean more allowed regions that we can look for. And as we can see here, it's not covered by any experiments that were previously taken. And in this range of the GeV, some GeVs, is constrained mostly from collider search. So this next generation electron positron colliders would be a great thing for in looking for this kind of processes, this kind of particles. And yes, it's basically it. Any questions? Go on.
I have a little doubt because you mentioned that there could be some decays to sharp quartz. To quartz.
Yes.
I have a little doubt because I was thinking that if decay to quartz, so the quartz are gonna be free, but as far as I know,
No,
the
no.
quartz are always in
Oh, no, sorry. It would decay in quarks, but the quarks will not be detected free. It will hadronize, so it produce jets. I mean, but we normally don't say we decay in jets because it's specifically the charm quarks, but the charm quarks will hadronize, and what we will detect are jets, not the free quarks. So if no more questions, let's thank the speaker again, me. And thank you for being here and our second presentation. See you next time.